So for each one of those eigenvalues that we found, there is an associated eigenvector. Okay, today we'll talk about how many eigenvectors can you have if you have a root of the polynomial, characteristic polynomial of some multiplicity. Now, what did I just say? What is the root of a characteristic polynomial? How many people lost me when I uttered that sentence?
Those are just the eigenvalues, right?
Yes, that's how we find the eigenvalues. That's correct. But what's a characteristic polynomial of a matrix? How did we find the eigenvalue? So we have these steps, right? So let me just skip here a few slides forward. So let me just remind you of the steps. So we talked about this geometric interpretation of what eigenvalues and eigenvectors are. And we have this procedure that's summarized here on this slide. So we started with an n by n matrix. And remember, all the matrices in this part of the course are now square. It's an n by n matrix, some matrix we'll call A. And then we computed the determinant of this matrix here, A minus lambda I, which is an n by n matrix. It is the original matrix A with lambdas subtracted from the diagonal. Now, a determinant is a function that associates some number to a matrix. Okay, so we computed the determinant of this matrix, A minus lambda I. Well, that number is expressed in terms of lambda, right? So that determinant of that matrix, A minus lambda I, turned out to be some expression that depended on lambda. Correct? Am I correct? Do people remember it the way I'm saying? Okay, so that was a character. So that expression in terms of lambda was something we called characteristic polynomial in lambda of this original matrix A. Then we found the eigenvalues by looking at the roots of the characteristic polynomial. That is, we set that expression in lambda, which was a polynomial in lambda, to 0, and found which lambdas make that 0. The lambdas that made that characteristic polynomial 0 were exactly the lambdas that made this matrix, A minus lambda I, singular. That's how we found the lambdas. We set its determinant, the determinant of A minus lambda I, to 0. That's what we mean by A minus lambda I being singular. Its determinant is 0. And those lambdas that make that determinant 0 are the eigenvalues by definition. Okay, I hope all of this makes sense from last time. Okay, then we so suppose this is an n by n matrix, and suppose in a nice case, we'll find these n distinct eigenvalues, right? Okay, they don't have to be distinct. Again, we'll see examples today when those eigenvalues are not distinct. We'll still end up in what we'll call a nice case, even when the eigenvalues are not distinct. But if the eigenvalues are distinct, then we'll get n independent eigenvectors. With the eigenvector, when we look at the set of eigenvectors, where each eigenvector is an eigenvector associated with a given eigenvalue, we have n eigenvalues. With each one, we have an associated eigenvector. We have a set of n eigenvectors. Those eigenvectors will end up being independent eigenvectors, forming a basis in Rn, in this n-dimensional space. Okay. Okay, so we'll go through a couple of examples just to make sure that all we just said, this was a brief review of this entire problem. We'll do a couple of examples today. Okay, so we gave a geometric interpretation of these eigenvalues and eigenvectors also. We talked about eigenvalues being these stretch factors, and eigenvectors being those vectors that don't move under the linear transformation that's expressed by the matrix A. So we'll talk a little bit about linear transformations again, going back to the first lecture on linear algebra. So A represents some linear transformation. We looked at the pictures. What is a linear transformation? It's some function that's applied to a vector, out comes another vector, and those vectors that stayed put, that is, those vectors that stayed on their own lines under this transformation, were the eigenvectors, and the eigenvalues were the stretch factors. Okay, this is all a review. So the plan for today is to look at something that we'll call matrix diagonalization with the use of these eigenvalues and eigenvectors, and how to quickly compute the powers of matrices. Okay, that's the goal. And then also to return to this idea that linear transformations are represented by matrices. In fact, what we'll end up saying is that every matrix represents a linear transformation. But remarkably, conversely, every linear transformation, which we'll carefully define what a linear transformation is, every linear transformation can be represented by a matrix. So that what this means is that if you know matrices well, you know linear transformations well. Okay, and conversely, if you know linear transformations well, you know matrices well. They're one and the same thing under this interpretation. Okay, so now let's remember this. So I'll return to that point a little bit later. Fine. So I think this one we did last time. So the matrix that's on my screen, what are its eigenvalues and eigenvectors? In fact, I don't know, you guys found your favorite software somewhere on the internet, probably some web-based software that allows you to quickly get eigenvalues and eigenvectors, right? Maybe some people have favorite software. The quickest, if you're familiar with Matlab, actually, let me bring this up. Here's Matlab. Let's fire it up. I don't know if you can see it. So I'll keep that on the background. So we'll allow us to quickly compute. We'll do this by hand also, but now obviously you're not required to use Matlab. It's just, for me, it's just a calculator. So I'll verify what you tell me in 1 second. So by the way, this is how I'll do the exam questions, right? So verify this in Matlab, make sure everything's correct so that your answers are correct, your submissions are correct. It's quick to verify in Matlab when you claim that your answer is something. So Matlab is convenient because even when a given problem has multiple answers, we found that Matlab in the past was helpful to verify whether your answers are correct, even if our own solution says something different. Okay, but anyway, let's put it aside. So what were the eigenvalues and eigenvectors of this matrix? Okay, and I'll be verifying this. This is, okay, so let me create real quick a little bit of a new script here. So here's going to be my little matrix. Oh, I need a keyboard, of course. Useful, that will be useful. Let me put that aside. So while you're telling me what the answer is, I'll be verifying this here on my screen. So my A is going to be a matrix. Looks like, what did we have? Oh, you guys don't see this, right?
We can see the Matlab window.
Okay, so my matrix was 0, 1, I think 1, 0. That's my matrix, right? So this is, let me just run that. So here's my matrix A. I can run it at the command prompt. Now what I'd like to do is I'd like to find its eigenvectors and eigenvalues. So I'd like to figure out what the characteristic polynomial of this thing is. Okay, Matlab, by the way, has a command. I mean, if this is for only those who are familiar with Matlab, it's called poly A, and it gives you the coefficients of the characteristic polynomial. I think it's roots, if I'm not mistaken. I haven't used Matlab in a while, but if you say something like roots of poly A, right, it will give you the answers. These are the roots of the characteristic polynomial. Let me just actually show you what the characteristic polynomial is. It's no fun to just simply say, I think it's polysum. I was checking that, or poly2sum, they might. Let me just show you. Of poly A, I think that's the way it is. So don't poly. You can check this quickly on their website now if you want to. Okay, so poly2. So what is this? Oh, it's not sum, polysim. Not sum. Okay, so x squared minus 1, right? So x is my lambda. Let me clear the screen so that you can see. Okay, x squared minus lambda. So what are the roots of this polynomial? X squared minus lambda. So how did I get this polynomial from this matrix? This is my original matrix. Did people remember? How did you find it? How did you guys find it? What did we do? The last time we did it by hand. This time I'm verifying what by now you know how to do by hand, right?
You subtract lambda from the diagonal and then find the determinant?
That's exactly right. And I get this characteristic polynomial. Sometimes it's hairy to find the roots of it, but you can always verify what the roots of this are. Well, x squared minus 1 has 2 roots. 1 minus 1, well, 1 and minus 1 are the roots of this characteristic polynomial. Okay, so those are the lambdas. Now, for each one of those roots, minus 1 and 1, I want to find an eigenvector, its associated eigenvector. So last time we looked at this transfer. By the way, what did this transformation do last time? Do you remember the effect of it? As when I view this matrix as a linear transformation, as something that represents a linear transformation. Do you remember the picture that we got? What did it do? What was the effect of this? We called it a permutation matrix, right?
It reflects it across the line y equals x.
Exactly. Another name, by the way, for this matrix is a reflection matrix because it reflects the vectors around the 45-degree line, right? Now, in Matlab, there's one very, very convenient command that says, I think it's either eig or eigs. Eigs, I forgot. So let's test. Eig A, okay, these give the eigenvalues and eigenvectors. But this command is even better. You can store the return value of this Eig function into these vectors, into this pair of matrices. Let's call it V and L, I guess. Okay, so, okay, this is not too good. Actually, let me try something else. I think it's easier. This is all correct. So here's what Matlab returns. It returns two entities, two matrices. This L matrix that I called L, this matrix that I called L here, returns the eigenvalues on the diagonal. It just returns it that way. Okay, so it returns a 2x2 matrix. I passed in a 2x2 matrix. It returned me a 2x2 matrix, and that 2x2 matrix has on its diagonal the eigenvalues as entries. Now, for the first column, for this -1, 0, that is for the first eigenvalue -1, this guy gives me a corresponding eigenvector. So this column is the eigenvector corresponding to this eigenvalue. You will notice that it is not, nicely scaled. I'll show you how to scale it nicely in a minute. Just to get, this is the same as -1, 1, right? If you scale it correctly. The second vector, I have identical entries in the entire column. This is like, I could have written it down as 1, 1, because any multiple of this column vector is an eigenvector for A. So whether I take it 0.7, 0.7, or 27, 27, or 1, 1, that's going to be an eigenvector. So Matlab has this convenient box. Like if you did this in Python, by the way, you can do it. Same thing, really, but you have to install all these libraries and so on and so forth. It can be a pain if you have to figure out which library to use, blah, blah, blah. So I think with Matlab, it's a little easier to use. You can create from this matrix, by the way. Here's my matrix A. You can make this matrix sim A, right? Make it a so-called symbolic matrix. And then you can have these V and L still call the same function called Eig of A, but now in a symbolic matrix, Eig of A, if I'm not mistaken. And this will return it much nicer looking entries for my eigenvectors. So notice again, 1, 1 was the eigenvector associated with the eigenvalue 1. And -1, 1 was the that's the 45. So these are 45-degree lines. So that 1, 1 vector here is that 45-degree line across which were reflected the vectors last time, right? The -1, 1 is that 135-degree line across which the other vectors are reflected. That corresponds to the eigenvalue -1. So we did all of this by hand. And of course, I was asking in the homework assignments people to do always this by hand. And if you have your favorite software like Matlab here, or Python, if you're adept to using those libraries, which do exactly the same thing, then you can verify all your solutions by hand in that software package. And I'm sure there are also like web-based calculators out there somewhere that do the same thing for just quick computations like that. So actually, let me copy all these commands here so that then later I'll copy paste to save some time. So let's call this. I guess let's call this example 1. Then we'll have other examples. And I think this is what we found useful, this command. So I'm going to copy this here. We also found what command's useful. Okay, so this guy was useful so that later I copy paste it. Factor B was a useful command. Okay, so I don't want to spend time now. These are I'm just copying here so that I can copy paste them later. So let me clear my screen and get back to the slides. You guys can see, okay, did people check in? Okay, so let me end this check-in then. Now let's get back to the slides. The slides are where? Here, somewhere.
Oh,
yeah.
I was checking in, sorry.
Sorry, one more time?
I was checking in, sorry.
I cannot hear. That's my computer here.
I was checking in, sorry.
Check in. So please email me then if you forgot to check in. Now I've ended the check-in. If I reopen it, it will add another column to the entire entry. So please email me and I'll manually have to enter your presence then.
Okay.
After class. Okay. So back to the slides. This is again a summary. Again, boy, this is for the general n by n matrix, A minus lambda I. We write down the determinant. The determinant was that. And these are now factored polynomial, factored characteristic polynomial that gives you the roots exactly, which is one command in Matlab. Okay, so in real life, you use a software package, right? Okay, so what else did we cover last time? So we made a couple of observations about eigenvalues and eigenvectors. We said that the product of eigenvalues was the determinant of the matrix, remember from last time? And the sum, what was the sum of eigenvalues?
Trace of the matrix.
Sorry, one more time?
Was it a trace of the matrix?
Yeah, trace of the matrix. Yeah, let me get my sound here. That's my fault completely here on this side, so my sound isn't. Okay, so that is correct. So the sum of the eigenvalues is the trace of the matrix. So we can check it with that example here in Matlab. For example, what's the trace of this matrix? 0. What were the eigs of A? What were the eigs of A? Okay, so what were the eigs of A? Where the eigs of A? Minus 1 and 1. Minus 1 and 1 sum up to 0. The trace of this matrix, 0, is the sum of the eigenvalues. Okay. What is the determinant of A? What's the determinant of A? What's the determinant, by the way, real quick?
Minus 1.
Minus 1, exactly. So you can check the determinant of a matrix. If you have a larger Harrier matrix, this one is easy to compute. You plug into your software, verify that your computation and your homework assignment was correct. So on the quiz, you'll be doing it by hand, but it's nice to have a software package to verify these things. Okay. So here's a justification on the slides of why we actually talked about this last time, why the determinant of a matrix is the product of its eigenvalues. We didn't prove it, but we sort of gave a hand-wavy justification that lambdas being the stretch factors in the directions, the eigenvector directions, the determinant being what? The volume of what? Of the box into which, under the linear transformation of A, the unit vectors, the perpendicular unit vectors in the original space Rn were transformed by A into some box. The volume of that box was the determinant of the matrix. Okay, this is no justification. This is no mathematical proof, but it gives some intuition behind the fact that the product of eigenvalues is the determinant of the matrix. Right? Any comments? Did somebody say something? Okay. Okay, so what are the eigenvalues? What's the product of the eigenvalues of these? Just to check. It is asking me to find the determinant of A. The determinant is going to be 1 times 4 minus, we can do it without writing it down, 1 times 4 minus 5 times 2, right? So 4 minus 10, that's going to be minus 6, right? So let's make this, okay, so let's call it example 2. So now my A is going to be what? 1, 2, 5, 4. 1, 2, 5, 4. Okay. Okay, so 1, 2, 5, 4 is now my matrix A is now 1, 2, 5, 4. What is its determinant? Determinant of A. Minus 6. It's the product of the diagonals, 1 times 4 minus 5 times 2. What is the slide asking me also? What is the sum of the eigenvalues? It's the sum of the eigenvalues. What does it have to be? The sum of the eigenvalues. Just help me out, please. What's the sum? Okay, this one is asking about the product of the eigenvalues. We determined that the product is minus 6. The product is the same as determinant. Okay, so let me write it down so that people just see it, what it is that I'm talking about. So product of eigs is that of A. That of A, which is minus 6, right? Now the question, what is the sum of eigenvalues? What is the sum, please?
Shouldn't it be 5 because that's the trace?
Yeah, that's exactly right. Should be 5. Equals 5. Equals trace of A. Trace of A. And I don't know if trace of A is a command or tr of A is a command. But yeah, well, trace apparently is a command in that. So it tells me Okay, so it tells me that's that. And of course, okay, so then what are the eigenvalues before I compute the eigenvalues here in a second? So I have that the product of the eigenvector, so I don't notice what I'm doing. I'm computing the eigenvalues and eigenvectors without computing the characteristic polynomial. I could do it. I could just compute the characteristic polynomial here, but I'm not doing this because I know that the product of eigenvalues is -6, and the sum of eigenvalues is 5. Well, what are the eigenvalues?
6, -1.
Yeah, 6 and -1. So let's check. 6 and -1, right? It's exactly right. 6 and -1 have to be the eigenvalues. These are the only two numbers whose product is -6 and the sum is 5. Okay, you can solve it. It's an equation if you'd like, just to figure this out. Okay.
I had a question. So 2 by 2 matrix has only 2 eigenvalues?
Yes, at most, in fact. At most. Well, it has exactly 2, but the eigenvalues could repeat as in the first example, right? The 2 by 2 matrix, this first one, remember this 0, 1, 1, 0 example, this example here, this one, this example here, it has 2 eigenvalues. Oh, okay, so this one has distinct eigenvalues. Sorry, but you can have. We'll give an example in a minute of the 2 by 2 matrix having an n by n matrix will always have n eigenvalues, but not necessarily distinct. Okay, so we'll see an example. It's coming up in the slides here. Okay, so but it can not have more than n eigenvalues. So every matrix, every n by n matrix has. Actually, it has exactly n eigenvalues. Why? Because this follows from the fundamental theorem of algebra, which says that any n-degree polynomial has exactly n roots. Now, some of those roots may be repeated. That's another question, but it does have exactly n roots. And therefore, every matrix of size n will have n eigenvalues, some of which may actually repeat. Now, okay, so can I ask you this? Why is it that a matrix, I guess the answer is the answer on the screen. My claim is that if a matrix has a 0 eigenvalue, then it is not invertible. So please help me out with this. Okay, so maybe the slide is not clear. So maybe, okay, so can people explain to me? So if one of those lambdas is 0, and then I'll ask you if this is an if and only if statement. Maybe it's easy to see it one way and not the other. Okay, so let's take a look at this example. Okay, so anyway, no, we just did this one. So here's the claim, and I'll ask you why that is. So consider this example here, 9, 2, 0, 0. What's the determinant of this matrix? Okay, so well, what's the determinant of this matrix? You can tell me this without, was it 9, 2?
It's 0.
Yeah, right.
It's 0, right? So how can you tell that it's 0?
Just calculate the 9 times 0 minus 0 times 2. So,
Yeah, that's one way you can plug it into the formula, but it also has a 0 row, right?
okay.
Right?
So it's a singular matrix, and singular matrices have all determinant of 0, then they're not invertible, right? So that's
Yes, exactly. That was exactly my question here, going back to the slide. So this one is not invertible because it is its determinant is 0. Okay, right? So that's an equivalent definition of singularity. We could have defined matrix to be singular if its determinant is 0. It's an alternative definition. Now, this one, if you look at its characteristic polynomial, you'll see, so what are its eigenvalues? Here's what are its so here's the characteristic polynomial. I can compute this by finding the determinant of this, or I can rerun these commands here, and this will tell me. So what is my P? That's not that A. So I want to run this A, and now I want to run this A. And what I'd like to do is I'd like to run this command. Okay. Oh, okay. So why my poly didn't work. Oh, okay. So I don't want to spend time on this, but okay. So here it is. So so here's you can factor this. Let me factor this. So what are the polynomials? So lambda and x minus 9. What are the roots? Roots of p then?
0 and 9.
0 and 9. Okay. Let me just see this on the screen. Sorry about that. Roots of poly A. 0 and 9. Right? Do people see my screen? I don't know if you guys can see my screen, but 0 and 9. So this is where this comes from. So 0 and 9, these are the roots of this characteristic polynomial. Okay, now let's do actually this one. Maybe we should do on I should switch. So I hope people have noted this matrix. Now we'd like to do that. We'll verify this in Matlab again, but let me switch to my tablet for a second. So now new screen share. Okay, so this is the matrix that we are talking about. This is the matrix that we're talking about. Okay, this is the matrix that we're talking about, and here's its characteristic polynomial. So now I want to find the eigenvalues for this matrix. What are the eigenvalues associated with a minus lambda I? Okay, so what are the eigenvalues associated with this?
0 and 9.
I'm sorry, the eigenvalues, that's 0 and 9. That's right. Lambda 1 is 0. Lambda 2, I'm asking for, this is my lambda 1 is 0. What's the eigenvector associated with this? Eigenvector with this, associated with this lambda equals 0. What am I solving? Am I solving this one? Am I correct?
Yes, is it minus 2 over 9 and 1?
Yeah, you set x2 to 1, x2 set to 1, and then x1 is going to have to be minus 2 9ths, right? Am I correct? Is that what you said? This is the eigenvector. Okay. Now for this different eigenvalue, lambda 2 equals 9, lambda 2 equals 9, what's the eigenvector associated with that? So the question will be, are these two guys, these eigenvectors, linearly independent? The answer will be yes, they will be pointing in separate directions. So what matrix should I be writing down here? So this should be clear now. So, right? So this, am I correct in writing this down? This matrix for lambda 2. I'm writing down always this matrix. For each one eigenvalue, I'm writing down a minus lambda I matrix. Right? So what is the answer to this?
0 1.
0 1 will work. 0 1 will work. So I'm solving. No, I'm sorry. So this is what I'm solving, right? 0 1. What did you say? 0 1.
Sorry, is that not the solution for it?
Wait. Okay. So you mean 1 0 maybe?
Oh, yeah, I did.
Okay. So yes, that's the eigenvector. Eigenvector. Associated with that one. So I have two eigenvectors pointing in separate directions. And of course, this is like, okay, so that's maybe it's, okay, that's an example. Okay, but there's nothing new. Now we want to do another example. So of course, if I went real quick, let me switch back to my Matlab. And of course, if I did this thing, then okay, this is pretty bad. I want to show you a nicer way of doing this. This, and then this. So that way, you see, I don't know if you guys can see my screen, but minus 2/9 and 1 was the solution that you gave for the first eigenvector associated with the eigenvalue 0, and 1, 0 is the second eigenvector we just found associated with the eigenvalue 9. Okay, so it makes sense to look at Matlab code, because even if other software packages that you'll find do roughly the same thing, it's just maybe the interface may look slightly different. Okay, back to our slides. Okay, actually we can do it through slides, and I'll switch for an example again to my tablet. So that we found out, this example. Now we want to understand when we have a basis of eigenvectors. In the examples that we've seen, all those two eigenvectors, for example, in the example just seen in a 2x2 example, those two eigenvectors were pointing in two separate directions. Those were linearly independent eigenvectors. But will this always happen? Will you always get linearly independent eigenvectors? And the answer is no, but most often you will. So what we want to do is understand the conditions under which we'll get those linearly independent eigenvectors, because that case is nice in the sense that it allows us, for example, of many things, one of many things, to compute the powers of the matrix very, very quickly. And we'll talk about that soon. Looks like we're running out of time. Okay, so here's an example. Okay, this we want to skip. Let's take this example. What we'd like to do is compute the eigenvalues and eigenvectors of this matrix. Can anyone tell me what the eigenvalues are just by looking at it without doing too many computations while I verify the answer that you give me here? Let's call this example 4, and our matrix is going to be 3, 8, 0, right? Now this time it's going to be 3, 8, 0. The second row is going to be 0, 3, 0, and the third row is going to be 0, 0, 3, 0, 0, 7, right? So this is going to be my new matrix now. This is my matrix A. So what are its eigenvalues real quick of this matrix?
3 with a multiplicity of 2 and 7.
Okay, so that's okay. That's correct. So what if you were to write down the, what is this? If you were to write down the characteristic polynomial of this, what would it look like?
Lambda minus 3 times lambda minus 3 times lambda minus 7. Or you can have lambda minus 3.
Lambda minus 3 squared you can write down, right? You can write down a lambda minus 3 squared like I'm about to show you on the screen. So this one, if you factor this polynomial here, if you factor it, you'll have x minus 3 squared times x minus 7. So 3 and 7 are the two eigenvalues. So now let's find the eigenvectors associated with eigenvalues. Now I could do this by issuing a command, but that wouldn't be super helpful. I'm going to switch now to my tablet, and you're going to help me write down the answer. So the determinant apparently is going to be 3 minus lambda squared, 7 minus lambda. Of course, I can see it immediately. So lambda 1 and lambda 2, as you've just told us, this has multiplicity 2, this eigenvalue. Do I have two eigenvalues? Well, yeah, I have two distinct eigenvalues. That's true, 3 and 7. But really, I have 3 eigenvalues where 2 of those eigenvalues coincide. Sometimes this fact here, this fact is written as lambda 1 and 2, just combining like that. So 2 eigenvalues have multiplicity 2, the guys that are 3. Okay, 2 lambdas are 3, and then 1 is equal to 7. Now let's find the eigenvectors associated with it. And then just heads up, I'm telling you that I will change one entry in this matrix, and we'll see that the picture may completely change. So let's find the eigenvalue associated with this first eigenvalue, 3. Well, okay. So actually, let's start with the second, with this other eigenvalue. That's probably more, I don't know if it's more straightforward or not, but let's find this eigenvector associated with this 7. So what do I have here? 3, 8, 0, 0, 3, 0. 0, 0, 0. That's my matrix. This is my A minus lambda I, right? And what am I looking for? I'm looking for a vector, x1, x2, x3, that will be taken to a 0 vector under the influence of this singular, which has to be, this matrix has to be singular, under the influence of this singular matrix. So which one of those non-zero vectors is being squashed into a 0 vector? That's how I look for an eigenvector every time. So what's the solution? This is a redundant row, and I better
instead of 3.
Sorry, one more time.
Shouldn't it be -4 on the first element and the second one in diagonal? Because
Yes, I'm sorry. Yes, that's of course correct. -4, -4. That's 3 minus 7. Yes. Okay, so what's the answer? What's the free variable?
x3.
X3. So let's set it to 1. I could have set it to 10, but let's set it to 1. Then what does this have to be? The second one. 0. And how about this one? The first one.
It would have to be 0, 2.
Would have to be 0, 2. Okay, so that looks correct. So 0, 0, 1 is the one associated with this eigenvalue. How about eigenvalue? So that's 1. How about the other eigenvalue, the repeated eigenvalue? How many eigenvectors do I have associated with that? So now this other eigenvalue is 3. So what's my A minus I lambda I matrix? 0, 8, 0, 0, 0, 0, right? I get a 0 row there. And 0, 0, 4, right? Am I correct? Or am I completely missing the point? I'm solving this system of equations, right? So what's the free variable there now? Which one is free?
X1.
X1 is free, right? So X1 is set to 1, and the others have to be zeros now, right? Do people see that this is eigenvector? This is an eigenvector, right? And this one is an eigenvector 2, right? This one is an eigenvector 2. These are both eigenvectors here. This one is associated with this lambda. This one is a single eigenvector associated with this lambda. So notice I have just one eigenvector. Now let's see another example. I hope that's coming up on the next slide. Oh, we have a solution here. That's okay. Okay, so all the answers are on those slides. Okay, this one gives you the solution. Okay, this one gives you the solution that we just did. But now I'd like to change this slightly. I'd like to change this matrix to 0. So now my matrix A, let me see if I have a solution coming up. Hopefully not. So now A is 3, 0, 0, 0, 3, 7, 0, 0, 7. What's the characteristic polynomial of this matrix now? Should I be switching to my Matlab to show you? Or you can just simply tell me that this one has an indistinguishable from the first example characteristic polynomial. It has exactly the same characteristic polynomial. What's the characteristic polynomial of this matrix? Not this matrix, but this matrix, A. Okay. So what are the eigenvalues now? Still have a polynomial of degree 3. It's factored into lambda minus 3 squared times lambda minus 7. 3 has what's the multiplicity? This is called the algebraic multiplicity of a root of this polynomial. What's the algebraic multiplicity of 3?
2.
2. That's that 2. The algebraic multiplicity of the other is 7. Now I'd like to find out, well, what's the, now let's do the usual, A minus 7. So please compare it with the previous example. 7i is going to be minus 4, 0, 0, 0 minus 4, 0, 0, 0, 0. So I'm looking for this for the eigenvector associated with this eigenvalue. What is it? So I solved this system of equations. And what's the answer?
Zero, 0, 1.
0, 0, 1. So that doesn't seem to be super different from the previous example, does it?
Wait, but shouldn't there be a 7 on the second row, third element? Because we changed the matrix, right?
Oh, I'm sorry. That should be 0 rather. I changed this entry only, right? So, but the answer is that. So how about this other guy, 1, 2, lambda, the other lambda. So this is, notice this is very different from the previous example. So now what's my a minus 3i? It's going to be 0, 0, 0, 0, 0, 0, 0, 0, 4. Okay, so now what's the solution now? So in the previous example, we had one solution. Did we write it down? Yes, we wrote it down here. For this eigenvalue, I had this single eigenvector associated with it. For eigenvalue 3, I have one eigenvector associated with it. In a minute, I'll introduce the notion of a geometric multiplicity of an eigenvalue. Its algebraic multiplicity of this eigenvalue is 2 because of this polynomial. It goes as a power of 2 into the polynomial. But the question is, what is its geometric multiplicity, so-called geometric multiplicity? The geometric multiplicity is the number of linearly independent eigenvectors that I will have associated with a given eigenvalue of a given algebraic multiplicity. So here in this example, where are we? Here, right here. So what is the solution to this system of equations? This is the second eigenvalue here that we're talking about, x1, x2, x3. What I'd like to do is solve this system of equations to find the eigenvectors. So what is my pivot? What are my free variables? How did we solve this from on day 1 or lecture 1? How many solutions do I have to the system? So please help me out. I know I can see the solution on my screen, and in Matlab, actually, I don't see it. So let me just actually do that. But I want you to help me out.
So x3 is the pivot, and x1 and x2 should be the free variables.
Exactly. So what are the, now I'd like to, that's right. So how many linearly independent solutions would I have?
Infinite?
Well, I have infinite in every case. In the previous case, I have an infinite number of eigenvectors. Okay, so just to make sure we're all
right. So long as they fall on the same line.
Yeah, they're infinite. There was one
like...
here, there was one eigenvector in the previous one, right? Am I correct? One eigenvector in the previous one. Here in this, I have 2 free variables. The number of free variables is what? The number of linearly independent vectors that form the basis of the solution. Remember on day 1, that plane, the plane being the solution to the system of a 3x3. Do people remember this? Okay, so let's write down the solutions. We wrote down the solutions as a linear combination of, as a linear combination of 2 linearly independent vectors. So let's set x1 to 1. Then what does x2 to 0? Then this one has to be 0. That's one solution. Is this a solution? Am I correct? Am I correct that this one is a solution? This is 1. Am I correct that these 2 guys are solutions to this system of equations? Or should I return to the Gaussian elimination to see how we wrote these down? And then we said that some linear combination of these 2 vectors is going to form the solution. Is it clear that any x of this form is a solution to this system of linear equations? Are we on the same page with this? Because that's the point. The point here is that we have, unlike the first example where this entry was 8, in this example, for this matrix, where that 8 entry I've changed to a 0 entry, I now have to this eigenvalue of algebraic multiplicity 2, I now have 2 independent eigenvectors corresponding to it. That means that the geometric multiplicity of this root of this eigenvalue is also 2. In the first case, the geometric multiplicity was 1 of the eigenvalue with algebraic multiplicity 2. In this case, the geometric multiplicity is also 2 of the eigenvalue of algebraic multiplicity 2. Okay, so that was the whole point. Now, I'd like okay, so let's skip this. Here's a justification of the fact that whenever you get linearly independent eigenvalues, you will always, whenever you get distinct eigenvalues, you will always have linearly independent eigenvectors. It's easy to show. Here's a justification of that. But as the last two examples show, whenever you get repeated eigenvalues, that is, what does that mean? That means that not all eigenvalues are distinct. Okay, so we had 3, 3, 7 were the eigenvalues in the last two examples. 3 and 3 are not distinct. So some eigenvalues coincide. Whenever you have coinciding eigenvalues, that is, not all of them are distinct, sometimes you can get all linearly independent eigenvectors corresponding to those eigenvalues, which was the latest example. Or sometimes you may not get linearly independent eigenvectors, 3 linearly independent eigenvectors, as was the case with the example just before this one, for the matrix 3, 8, 0, 0, 3, 0, 0, 0, 7, for the previous example, right? Does that make sense, what we just said? So that was like one of the major points of today. And now we have to move on.
Wait, what were the eigenvectors on the previous example?
On the previous example, let me just bring up Matlab, just to be clear. Okay, so here's my cheat sheet. The first, example for A is going to be this with 8 here. And example, so example for B, sorry, this is some way here, is going to be this matrix with an 8 here. Okay, so let's find the eigenvalues and eigenvectors. Let's start from this matrix, just to recap. This is how many eigenvalues do I have all the time? For both of these matrices, what are the eigenvalues? Recapping, what are the eigenvalues for both of these matrices? What are its eigenvalues right now?
So they're the diagonal elements?
3, 3, 7. 3, 3, 7. Let me do the symbolic one. It's easier to see because you don't get. So here are the eigenvalues and eigenvectors for this matrix. Notice that I have these 3, 3, 7 here, but I was given only two eigenvectors associated with this. So geometric multiplicity of this eigenvector, of this eigenvalue 3, its geometric multiplicity is 1. Here's the eigenvector 1, 0, 0 that we found. That eigenvector is the only eigenvector associated with this lambda equals 3, which has the algebraic multiplicity of 3. However, if my A now is this, then not this, I'm sorry. If my A now is this with 0 here, this one with 0 here, then if you go find the eigenvalues and eigenvectors, you'll get 3 eigenvectors as well as 3 eigenvectors. So now notice that my eigenvalues are exactly the same, but I have 3 eigenvectors associated with them. These are linearly independent ones. If I were to compute the determinant, its determinant is not 0. These are linearly independent column vectors. This V's columns are linearly independent. Its determinant is not 0. Right? Does that make sense? Okay, so that was like one of the major points of today. Now we have to go back and talk about, finally, what we wanted to talk about. I don't know if we can talk about through these slides, just to save time. Okay, now what we'd like to talk about is matrix diagonalization. So here's the idea. We can turn this, any matrix A whatsoever, into a, we should do it on the slides because just looking at this, you'll be just confused with the clutter of the symbols. So let me just switch to my tablet. So here's the thing with these Zoom lectures. We end up, okay, I mean, I wouldn't say we're inefficient, but we do lose a few minutes here and there all the time. Okay, now we'd like to get the matrix diagonalization. And with this matrix diagonalization, there are a few things that I'd like to mention here. You're given list any matrix A. It's an n by n matrix. Want to simplify somehow this matrix. Let me ask you this. What is going to be, let's forget about what you see on the screen right now. What I'd like to ask you about is A times S. S is so let's take a simple case where this A has all eigenvectors of A are distinct, and I have n eigenvectors x1, x2, and so on, x of n, all these distinct eigenvectors of A. And I put all these distinct eigenvectors of A into this matrix that we call S. And I just simply give it a name. Take all the distinct eigenvectors and put them like side by side as columns and call the resulting matrix S. My question is, what happens when I multiply this matrix from the left by A? Okay. What do I get? Let's look at this column by column. So what happens when I multiply this A by this first column, x1? What do I get? It's an eigenvector. So what does it mean to multiply A by the eigenvector?
You get a stretched version or compressed version of it.
Exactly. Do I get lambda 1 times x1? Right? I stretch that vector, lambda 1 times. What do I get? So I'm writing down the product of a matrix by a matrix column-wise. So I'm multiplying by column. So A times the first column is going to be this column. A times the second column is going to be this column, right? So what should I write down for the second column here? We're taking a simple case. These lambda 1, lambda 2 are distinct eigenvectors, let's say. As we'll see, they don't have to be. Lambda 2, right? Am I correct? Would I get that? Would I get lambda n xn column vector here? Am I correct? Everyone's on the same page. Now let me copy this for a second. I'd like to write it down here. Okay. Need extra scratch paper here. Please, for 1 second, ignore this example. We'll do a 2x2 example to make this clear in a minute. But I want to continue writing this. What would I have? Can you, would it be correct if I rewrote this like that? X1 times, sorry. Okay. Am I correct if I said that this is x1, xn, multiplied by lambda 1? Do people see? And a bunch of zeros here. There's actually a bunch of zeros here. Lambda 2, bunch of zeros everywhere. Lambda n. Do people see that just multiplication-wise, matrix multiplication-wise, this is the same? Do people see this? Again, this is the matrix S here. Do people see that what I've just written down is A times S equals S times this matrix that has a bunch of lambdas on the diagonal? It's written in exactly the same way Matlab was giving me all these answers. And by the way, this is part of the reason why Matlab finds it convenient to store these just lambdas in this matrix. Those entries are zeros all the time, except for the diagonal, where you have a bunch of entries like lambdas there. Let's call this matrix lambda, like big lambda like this. It's Greek capital lambda. You see that this is an identity. It is an identity. Now, because these eigenvectors, I'm assuming, now none of this will work if A didn't have linearly independent eigenvectors. But we assume the simple case, which we didn't have to, but we assume the case where the eigenvalues were distinct. In which case, what happened is that my eigenvectors were linearly independent. And why did I make a big deal out of this all this time? Because if these eigenvectors are independent, this matrix S, does it have an inverse? Can people help me out? Does S have an inverse right now? With the assumption that all lambdas were distinct.
Yes, it does have an inverse. Right?
It does have an inverse. So I can multiply both sides by that inverse of S. and I get lambda here. Do you agree that I can multiply that? And now comes the magic. So all of this buildup was for the following magic. Now I want to compute. So first of all, people do agree with this. And you can also agree that I could multiply this expression here by S inverse to the from the right as well, to get that A equals S lambda S inverse. We'll do example in a second. Right? Do people agree that this is correct if S has an inverse? Now comes the magic, finally. All this conversation was just for this. I have this. Now I want to compute the power of A. So here comes the kicker. What is A squared? A squared is going to be S lambda S inverse multiplied by S lambda S inverse. Am I correct? Or am I lying to people? Right? I'm absolutely correct. And because of the associativity of matrix multiplication, I can place the parentheses any way that makes me happy. And the way that's going to make me happy right now is going to be this way. Okay? Lambda S inverse. What do I get? And this is the magic. This is what we're building up towards. The product of these matrices is the identity matrix I. And therefore, this product ends up being S times lambda squared. This is that lambda times that lambda, which is easy to compute. Lambda is a diagonal matrix. It has a bunch of zeros only on the diagonal. It has non-zero entries. So that's lambda squared S inverse. People see the magic, and why am I saying that this is magic? Because if I compute the third power of the matrix, do I want to do that computation computing the power of matrix that we started this class with when we first saw algorithms? And we saw that matrix multiplication was an n-cubed algorithm. If you have a huge matrix, you will never complete computing it. Let's see what A cubed is. See how this notion of eigenvalues and eigenvectors simplifies this computation. So what happens? Do you see that this is going to be this? And now I'll be asking you, why is this simpler? So why exactly is this magical? What is the savings in computation? Do you see that nth power of this matrix is going to be S lambda to the n, which is easy to compute because lambda is a diagonal matrix. What is the nth power of this matrix? 15th power of this is simply this matrix. I compute the powers of just simply the diagonal entries. These entries will be zeros. Easy to compute. You're computing powers of two numbers as opposed to computing the power of a matrix, 15th power of a matrix, which is costly. Nobody wants to do that. The nth power of this matrix now, to compute the nth power of A, I have to do I have to compute the eigenvalues and eigenvectors of A once. Then I have to invert this matrix of its eigenvectors. I do have to compute S inverse, but just once. I do have to incur this cost of computing the inverse of the matrix. And of course, all of this works provided that S inverse exists. If it doesn't exist, then all of this fails. Then we'll have other decompositions to help us out. Okay, but this eigenvalue decomposition is the nicest decomposition when you have n independent eigenvectors. This is the decomposition. Eigenvalue decomposition spectral. This is called spectral decomposition because lambdas are the collection of lambdas. Sometimes in some contexts in nature are called the spectrum of the matrix. Also, just another term. We'll call them eigenvalues. So this is called also the spectral decomposition of matrix A. So all you have to do is compute the inverse of matrix S once, and then compute the nth power of the diagonal matrix. Easy peasy. And then compute the product once, and you have the nth power of matrix A. Right? It's kind of this is nice. Okay, you should do a couple of examples now that you see in the slides that follow this. So this will be on the, you'll have a question like this on the final. So we'll do a little bit of a review of this on Monday. So please make sure that you go through these slides before Monday, and you have these questions in the practice sheet. So please practice with this. So make sure you understand this spectral decomposition of the matrix.
I have a question.
Yes.
So what do you do when the S is not invertible?
Oh,
because I think the problem on the practice problem was like that.
Sorry, one more time. On the practice
What do you do when
sheet,
S isn't invertible?
No,
Because on the practice sheet, I think the question was like that.
oh, was there a question like that on the practice sheet? I think I gave you all invertible. Okay, so on the practice sheet, you will probably see a question similar to the one that we discussed now, where you did have eigenvalues of repeated algebraic multiplicities, of algebraic multiplicities greater than 1. But the geometric multiplicities should also be greater than 1, so that you will get n independent eigenvectors associated with those matrices that you have on the sheet. So your S matrix, even though you might have repeated eigenvalues, your S matrix will be invertible. Now, back to the question: what if it's not? What if this matrix does not have repeated eigen? That does not apply to the practice questions, because in the practice questions, please, if you find otherwise, please let me know via email that you found that that matrix was not invertible, that that it would be impossible to find the n independent eigenvectors for one of the matrices given in the practice sheets. Please let me know that by email, because as far as I remember, all those matrices were invertible. Those are all nice cases there. But in practice, what do you do with this? There's something called singular value decomposition in linear algebra. Okay, so you should, that would be the next step when you continue with, say, data science. It's a useful technique used in data science today, say singular value decomposition. Now that also applies to matrices that are even non-square also. It's a decomposition similar to this. It's not as nice as this, but also has practical applications today with non-square kind of tables that today people tend to collect, right? When solving modern day problems. So yes, so the point is, the short answer is, if S is not invertible, none of this discussion applies. But there is a minor modification that we could make if we had more time and discuss something called singular value decomposition, where we could fix the issues, but not in this class. It's in more advanced classes, you'll discuss singular value decompositions, like specifically in a linear algebra class, or in an applied linear algebra class, or in a data science class, maybe. At least those classes that cover that care about the mathematical background and not just give you code. There are plenty of data science classes just teach you how to use Python libraries. That's not data science, right? Just have to understand the fundamentals as well. Okay, so that's the long answer to a question that I could just simply answer by saying, if S is not invertible, none of this applies, and none of the questions in the practice sheet should have non-invertible S matrices. If you find otherwise, please let me know, and I'll update this accordingly in the sheets. Any other questions?